Okay, I'm talking to Gary Wilson here, and he is interested in human resources, human services for his community, and he's going to describe what his problem is, and we're going to try to model or start building a model that can help him with his job as in human services.
Absolutely. First of all, just happy to try to use this process for a very important issue here in the state of Tennessee. I work for the Department of Human Services, and one of the services that we provide to our community is public service safety net benefits. And so some individuals who might be in some type of crisis may come to our office for assistance. Generally what happens is they may have some kind of economic challenge where they need services. The services we provide are generally things such as food stamps, also childcare, what's called TANF, vocational rehabilitation. And so they may flow into our system. And while we have them in our system, our goal is to return them back in a much better capacity than the way that they came in. And so we have programs and services that we deliver while they're in our customer base, all with the goal of moving them back to self-sufficiency and self-support. And so the goal here with this model is maybe to build the model showing the flow into our system. And then while we have them, a demonstration of building capacity that hopefully reduces the stock and flow out of the system.
Yeah, okay. I think we can work with this plan, and we can start building a model in Vensim. So let me share my screen, and I will call up my Vensim model. Let me just close this old model that I was working on. Close this and let's start a new model. So to start a model in building in Vensim, you hit File here and you hit New Model. And so then you specify the time. So Gary, would you like to use calendar time, or would you like to use just generic years or generic months or whatever? Would you like to
Let's
start in 2020 or 2010 and move from there, or would you like to just have 0 as the initial and 100 as the future? You can change it at any time.
Yeah, it would be great if we could model towards the future. So anything that models towards the future would be great.
Okay, well, how far do you want to go back in the past? Do you want to go like
Uh,
10
Maybe 3
years,
years, 3 years.
3 years? Okay, so we will start at 2020. And how far do you want to go in the future?
Let's go to 2027.
2027. That's interesting. Okay, well, that's a pretty short period of time. And I assume you want to go with years as the unit of time rather than months,
Correct.
or okay. So you want to use years. Now, one of the interesting things about system dynamics is that it's got this idea of a time step. And the time step is the way the program estimates the change in the behavior. So basically, it's going to walk through time, uh, in this case, 1 year at a time for 7 years. And that may be tricky because the idea here is that if you have a significant amount of time to change things, let's say things change over a few years, that this is not going to be a good way to do it. It won't give you accurate results. So you have to reduce the time step so that you can get an accurate result if you have a lot of time required to change things. So I'm going to set the time step to 1.25. The time steps are in units of 2 to the power, some negative power. And so I'm going to take 2 to the negative power 3, which is 1.25. So this is going to be 1.25 of a year, 1/8 of a year. So that's, you can change it to anything you want. Well, not anything, but you can change it to very low numbers if you want. And sometimes that's important to get accurate results. Anyways, I don't know if that's too confusing. Do you have any questions about that, Gary?
Well,
Okay,
that,
let's
that's
let's move
just
on.
one, just one question. Can you go back and show the time step again of all the options?
Yeah,
The one that's literally towards the bottom there is the one I select a lot.
yeah, that's not a problem.
Okay. But I
You
don't
could,
know I don't know, I've selected it not because I understand fully the logic as much as that's been the one that I've seen selected the most.
yeah. Well, that is a good one to get very accurate results. One of the reasons that I often chose a higher value is because I convert my models to Excel. And basically, each time step is a row in an Excel spreadsheet. So, if I have this very small time step, that's a many hundreds of rows to try to simulate in my spreadsheet. Whereas if I have a lower number, in this case, I would have 8 rows to cover a year of time, which is not
Understood.
too hard to handle in Excel. I don't know how many rows I would need for a year of time using this number. Probably a very large number. Anyways, that's just something we can talk about at a later date, is how you convert these kind of models to Excel. I find Excel useful for certain things like calibrating the model to real-time, real historical data. Okay, what I'm thinking of starting with is maybe a little bit different than maybe what you would think of starting with. I'm thinking of starting with something like the population, not just the population of the people you're helping, but actually the population of your community that you are responsible for. So this is like do you work by the total state, or do you work by the county, or do you work
State.
state? So, okay, this is, maybe I'll just change this to population of state. Population, I'll just say population. I won't say state. I'll just say population, and we'll assume we mean state here. And then, so then what I do is I would have an initial population, and that would be the population. And I use first letter capitals for stocks, and all capitals for parameters or constants. So I'm going to have an initial population, and that's the population in, I spelled it wrong. And that's the population in 2020. Okay. So do you have any idea what the population in 2020 was for the state?
State.
Yeah. Doesn't really matter. We can just put in a nominal
Let's
number
say
here.
7 million.
Okay. So we will put in the initial population is 7, and I generally put E6, meaning 7 million. And then I say this is going to be estimated in people. So this is people, because again, we'll show you that we need to make sure the units work properly. And so then we set the population to be equal. The initial value here is going to be initial population, and then we'll have people as the unit of the measure. Okay, so now we have to have a flow in. So we will have a flow in of of let's say we call it inflow, or I don't know. We'll call it births, I guess, and deaths. because we might also want to have net migration as well, but we'll maybe do that later if we think it's important. So we have two flows. We have births and deaths, and then we have a birth rate. So we will say we have a birth rate, and that's all caps. And we have a life expectancy, and that's all caps. But maybe in the long run, these things will change because they do change over time. But right now, we're going to assume they're constants. And if you have real data on the population of your state between 2020 and 2023, we can use that data to to calibrate the model, calibrate the birth rate and the life expectancy. So basically, the birth rate we'll put into the births, and the population we'll put into the births, and the life expectancy we'll put into the deaths, and the life expectancy we'll put in the population will put into the deaths. And then we will now say that we're going to figure out what these values are. So I'm going to start with population again. And this is now said that population is the integral of births minus deaths. So it's put in for you the formula for the population, the changing population. And the births is equal to the population times the birth rate. And this is in people per year. So we'll change this to people per year. And then we will have the birth rate. And when it goes clean like that, that means that it's got a formula in that variable. And now we have deaths life is population divided by life expectancy, and this is in people per year. And then we have birth rate, and let's just say that the birth rate is 1 divided by 70, and that's basically 1 over the life expectancy, and this is in terms of what they call people per year, which it can be simplified to 1 over years. So I made it 70 because I'm going to assume that the life expectancy is 70 years. And I'm going to put this as years. So now I have I have a working model. All of the variables are defined. And I can go here to the model and I can check the units. And it says units are okay, which is important because if you don't get them okay, it probably means that your formulas don't make sense. And then I can run the model, and so I've ran the model, and you should be able to see. Sorry, I have to run the model. Maybe I have to save the model first. So let's save it. So I will save it as Gary's model. I will save it as Gary's model. And I will save it. And let's see if it runs now. Yeah, sorry. Okay, so it's going to run. And now if I look at the population, we have a flat line because the births and the deaths are equal. So if you look, so basically I set up the model to be in equilibrium to start with, and you have births equal to deaths. So the inflow and the outflow are the same, and that means that the system is in equilibrium, which means the stock doesn't change with time. And I did that by making the birth rate to be 1 over the life expectancy, and this is a good technique to often start in equilibrium and then move out of equilibrium by changing the parameters. But one of the things you should also recognize is that is that if you want to understand what's happening, it's all about the inflows and the outflows. So, let's say we make the life expectancy equal to 72 years instead of 70, then we will see here that if we run it now, we'll see that the population, you can't really see it because it's such a short period of time and it's 70 years. But anyways, the idea, if you look here, you will see that the population does grow slightly with time. So it starts at 7 the E6, and you can see it's growing slightly. You can't see it in the graph, unfortunately, but you can see it that it is growing when you look at the actual numbers. And if you change the length of time that the model ran by changing the settings, let's say you put in 2050 here instead of 2027, and you run this, you could get a better view of the population growing. Well, maybe not. You still have so many people, I think, that it's just a flat line when you look at it from that perspective. But you can see the population grows quite a bit. Anyways, so let's change it back to 2027, and so I don't know. I don't know if this is all that useful because the population doesn't change very much over the period of time that you're thinking, Gary. So I'm not sure if we really need to worry too much about the population growing. But let's take a look now at your problem, and you have a stock of, what do you want to call these people in the stock? Do you want to call them customers, or is there a better word for it than customers?
Customers.
Customers is good.
Yeah.
Okay, customers. And then we will have now, generally I put the inflows on the left and the outflows on the right. So we will have an inflow of customers and an outflow of customers. And we will have now, we will say, well, another important thing to recognize is that you have to connect the stock to the outflow, because you can't have an outflow of customers if you have no customers. So basically, as the number of customers declines, the outflow declines. And so you have to connect the customers to the outflow, because if you don't, you could end up with negative customers, which of course is ridiculous. So you don't want to have that situation occur. So we need to connect this to, so let's put in, just for starters, let's put in the initial customers. Just generally, I like to set it up. You could start it from 0, and let's say we have a, what would be a good word for the inflow? Need for services.
Yes.
I'm going to make it a internal variable, need for services. And I'm going to say that we have a outflow of what do you mean? What's a good way to describe the outflow? Is it based on
Well,
maybe, what's that?
we could call it self-support,
Okay,
meaning they're able to support themselves at that point.
okay, that's great. That's great. Okay, self-support. Now that's interesting. So I think it's actually not necessarily self-support. It's actually the self-support rate. So this outflow might be self-support, but this is actually a rate of people who are able to support themselves. Does that make any sense, Gary?
It does.
Okay. Okay, now let's connect all this together, and we will say initial customers goes in here. And this time I'm just going to say the need for services goes in here. I'm not going to connect it to customers, but I am going to connect the support, and I'm going to connect the customers to the outflow. So like I said, you can't have outflow if you don't have customers. And the more customers you have, probably the more outflow you have. However, the inflow might be determined more by other things than the number of people in the system right now. Does that make sense, Gary?
Yes.
Okay. Okay, so let's actually put some formulas in. So okay, what do you think the initial customers we should use is?
Um, let's say, is this the flow of customers coming in?
No, this is the initial customers. This is the current number of customers in 2020.
Okay. Let's put that at 800,000.
Okay. And this is again people, which
Yes.
is good. And then we have this now customers is equal to the initial value is initial customers, and the flow is the inflow of customers minus the outflow of customers. You don't have to do anything there. And then this now is also in people. So this is the stock of customers. And then we have the inflow. And I'm just going to say that the inflow is the need for services. And that's just going to be in people per year. And then I'm going to say that the outflow is equal to the customers times the self-support rate. And so this is going to be in people per year. And then we have the need for services. So how many people come in per year to the need for services? How many people per year need services, would you say, on average, let's say?
Maybe 1 million.
Wow. Okay. Let's say 1 million people flow in, and that's 1 million, and that's in people per year. So those are the people coming in the door. And how long does it take to obtain self-support?
We're looking for an average.
Yeah, an average. Yeah.
Um, let's say 2 years.
Okay. Well, I'll say 2 years. Well, this is interesting, because like I said, when you have a small value in this what's called a delay or a rate, um, you end up with you have to have a very small value for the step size. So that's sort of why I chose a small step size. So this is now again in 1 per year, and this is basically for every 2 people, 1 person leaves per year. Uh, and then and that's also means that you have a 2-year support time. So does that make sense, or do you want me to change this to a self-support time?
No, that works.
Okay. Okay, now let's just check to see whether we've defined the model properly. So we will check the units, and the units are okay. So it looks like we're good to go. Okay, and then so now we can run the model. And one of the interesting things about running the model, I find, is trying to guess what was going to happen here. So any guesses about what you think is going to happen to this population of customers?
I think the stock's going to grow.
Okay, let's take a look. We'll run it, and we will look at the customers. Let's take a graph. Now that's interesting, eh? Do you see what happened there?
Yeah, we got exponential growth almost, isn't it?
Well, it's actually logarithmic growth. Yes, it grows rapidly at the beginning, and then it starts to reach an equilibrium after a while. And that I find that's interesting, because basically, what you've maybe reached is a capacity limit or something of the customers, that basically you get to a point where the outflow equals the inflow because you have so many customers that you're flowing out the customers, as fast as they're coming in because
Hmm.
you have so many customers in the stock. So if you flow them out, on a 2-year basis, you'll have so many customers going in the stock that you'll be flowing out 1 million people a year if there's enough people in the stock. And that equals to your inflow, which doesn't change. If you look at your inflow, you see that your inflow is a flat line. And if you look at your outflow, you see that your outflow should basically mimic your stock. So you see that eventually you reach 1 million people a year outflowing based on being in the system for 2 years. What do you think of that, Gary?
So that is interesting. So it almost produces a really opposite effect. Our goal is to move people to self-support, um, so that they don't need our services. And what's really interesting about at least what I'm seeing here, if I'm reading this right, is the more people that's in our stock, the more people we move to self-support faster. Is that what I'm reading?
You're not moving them any faster, but just
Okay,
because there's more customers, there's more people in the stock of customers, you're going to be moving a lot of them out, because
uh,
there's just a lot of them in there.
right.
And eventually you'll reach a point where the people you move out per year equals the total inflow per year, and that leads you to an equilibrium in the stock. Does that
That's
make sense,
interesting.
Gary?
It does. It does. I don't know if I would have seen that without this model showing that, but yeah, that is very interesting.
Yeah. So I think, what this tells me is that, if nothing changes, you really should, in the long term, think of having the capacity to handle 1 million customers.
Yeah,
So I think you can say, that, that really you can, if you can handle 1 million customers at the same time, I think you could reach a nice steady state in terms of you wouldn't have a growing situation.
got it.
Yeah. Okay. So that works. Now, uh now, I don't know I don't know if you agree with this, but I'm going to connect the births, which is maybe not a good thing to connect, but maybe there's a better way. Maybe we go from births to maturity and we have young people and adults and elderly. But I'm going to connect somehow the flow into population with the need for services. So as the population grows, there's more need for services.
Yeah,
So if I go here and I connect this birth rate, this number of births per year, to the need for services, and let's say I have, instead of just all the births, I have a value like, the fraction. I'm going to make it small letters. So I'm going to say the fraction. I should make it small letters. Let's say I'm going to say the fraction of 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 new people needing services. Okay. So I have this value, and now I'm going to say this is actually going to be connected to this variable, And I'm going to say something about this. So, so let's say we have a fraction of, let's say, I don't know, zero point 0.5. So we say we have zero point 0.5 of the new people in the state, or the new people somehow coming in. And this will be actually a dimensionless variable or a fraction. You can call it a fraction, or you can call it a dimensionless variable. So I'm going to call it a dimensionless variable. And basically, I'm going to say that we will say that the need for services is equal to the births, or the new people, times the fraction of people, of new people needing services. Okay. Does that make any sense, Gary?
It does.
Okay. So now I'm going to check the units again, because I think, like I said, we want to check the units every 3 minutes, and we want to run the model every 3 minutes. Okay. So now I don't know what's going to happen, but let's run it and see.
Can I guess?
Yeah, go ahead and guess.
So I think we're going to see the growth again. I think we're just going to see it growing faster.
Okay. I'm not sure what the births are, but let's just check it out and see. So if we see here, we'll probably see, my opinion, oh, look at this.
Wow, completely opposite of what I thought.
Well, that is only because there's not that many births. So basically the inflow is actually, the inflow is such here that you actually have more outflow than inflow up until the point where it gets to equilibrium. And you notice here again that this does not ever achieve zero. It only achieves close to zero. So basically, the less customers you have, the less outflow you have until you reach equilibrium. So what do you think of that, Gary?
So can you explain how the rate of births, that how it made the adjustment to the million people that were in need of service? Did the rate of birth just override that number?
Yeah, basically, we originally had a need for services here. This number here in the formula was 1 million per year.
Right.
And this was 1 million per year before, and that gave us this growing up to equilibrium of a well, this growing up to 1 million per year in the stock. And now we see that if we look at this need for services, we see that we have a flat line of people, and it's only at about 50,000 people if need for services, not 1 million anymore.
Okay.
So maybe, I don't know. Let's take a look at the births, and we'll see how the births look. Sorry, we'll look at the births graph, and we see the births are 100,000 births. So basically, maybe these shouldn't be called births. Maybe they're called, adults, or aging people, or something like that, maturing people. And we say that we have 100,000 maturing people a year, and those maturing people may need services. However, maybe that's not necessarily the best way to formulate the model. Let's take another view of it. This is just new people. So let's take a look. Let's take another way of looking at it, and we will say, just before we move into another way of looking at it, we'll say that this fraction of new people needing services is actually something that we might be able to affect with policies. So, for example, if we have some nice policies for the state, we might be able to reduce this fraction. Does that make sense, Gary?
It does.
Okay, let's try something a little different here, because maybe it's just not the new people that come in. Maybe it's just actually the whole population that can be affected. So I'm going to click on the garbage can here, and I'm going to delete this link. And I'm going to, instead of connecting births to the need for services, I'm going to connect the population to the need for services.
Mm.
Because this will say that it won't be just the new people that need services. It will be the people who are adults in the system. Actually, I'm going to change this variable to, I'm going to change this, if you don't mind, Gary, I'm going to change this from births to maturing, because I think you're talking mostly about adults, aren't you? Or are you?
Yeah, it is, but also our programs do serve adults with children,
Sure.
but it's
Well,
it's primarily the
I think,
adults.
yeah, I think we can consider that by looking at the average children per adult.
Okay.
So let's do that. So I'm going to say maturing here, and I'm going to say actually something like the the uh, I'm going to say the maturing time, and I'm going to say the maturing time is 40 years. I guess this doesn't make a lot of sense. I would need really I would need well, I'm going to go back and go back where I was before, because I would need a births into a population of children, and then a maturing from children into adults, and then possibly a maturing from adults into elderly. So that might be a better formulation of the population. So I'm not sure. I don't want to do that with this model right now. But let's say we have a population and it includes children. And so now we're going to say instead of the fraction of new people here, we're going to actually have another value is maybe we'll have a value of um, the the rate uh, or what would be a good phrase for this? Maybe the time uh, time uh, when time when services are required. So we have this idea of the time when the services are required. So we have a population, and and so these people are in this stock for say 70 years, and maybe at a certain time they may require services, and a certain fraction of them will require services at a current time at a certain time. So this might be the average time that people will need the services, and I'm going to connect this to the need for services. And the reason I need a time here is because the units of this is people, and the units of this is people per year. So I need a time here to say, what I'm going to do is I'm going to take this formula again, and I'm going to say that the need for services is now the population times the fraction of people and of people who need services divided by the time when they need services. And that gives me a nice formula which has people and years. And so now I'll close that. And then I need a years. So let's say, what year would you say that the average time people would come to need services? What's their age, would you say?
Their age
Yeah,
are you looking for an average age?
an average age. Yeah.
Let's say 32.
Okay, 32. And this is now years. Okay, so now we can run this model. Let's check the units again. That's what we always have to do. And we check the units and we're still okay. Isn't that great? And now we're going to run the model, and let's take a look at what happens now. So what do you think is going to happen? Any idea? We have a large stock of people, and we now have a 50% of them need help when they're 32 years old.
I think it's going to go up.
Okay, let's try and see. Down again. So let's take a look at need for services. So we have a need for services, and we now have about 110,000 people who need services every year. Um, so what do you think? Maybe the fraction is higher. So if we change the fraction to be, instead of 50%, we say 80%, maybe that will make a difference. So if we run this now and we see, we can take a look at customers, and we see that it does still decline, but maybe not as much.
Which, my batting average so far isn't that great, but it's great that I'm batting in the wrong direction, because that graph is what we want to see. We want to see
Right,
the decrease
right.
in customers for our services. And
Yeah.
so if I had to be wrong, I would love to be wrong in that direction.
Yeah. And so, I think, but it is important to understand why this is happening.
Sure.
And so, basically the reason it's happening is because the inflow is less than the outflow.
Right.
And the outflow is determined by the self-support rate. So let's change the self-support rate now to be a lot longer. So a lot more years. So let's say instead of 2 years, it takes 10 years to become self-supporting. That's pretty extreme, but let's see if that makes a difference. Okay, so now we see that the number is increasing because we now have an outflow that is less than the inflow, because it takes so much time to become self-supporting.
Mm,
Does that make sense, Gary?
it does.
Yeah. Anyways, that's just this is the other. Maybe we don't need all this complexity. Maybe we don't need the population here. I was thinking primarily of a growing population, which might have a greater need for services. But since we're only talking about a few years between 2020 and 2027, the population might not change that much. So the population may not be an important variable here. Um, but anyways, I thought in general it would be useful to look at the possibility of a growing population and therefore a growing need for services.
Yeah.
Okay, well, that's sort of a start of the model. We're running out of time here. So, anyways, what do you think? Are you happy with this? Do you want me to send this to you and you can fool around with it a little bit and see, change
Yes,
the
really,
parameters?
please. Yeah, I learned a lot.
Okay. And like I said, what we'll do, I think all we have to do now, I think, is look at what goes into this, getting this self-support rate down, and how do we get this fraction down? So what can we do in terms of policies to basically get the inflow down and the outflow up? And that's all we need to do.
Love it.
Isn't that amazing?
I like it.
Yeah. And but another thing I think is interesting here is the capacity. So for example, if we have an increase in the number of customers, this suggests that there's an optimal capacity that you need for your service providers to handle the customer base.
Right.
And I think that could be very informative to your leaders, is to know that if you do have a growing population of customers, that it's not going to grow forever. It's not going to grow exponentially, and there will be a capacity limit that you will reach, that basically you will have enough resources to meet the capacity. And then we can talk about, what it costs to provide that capacity. And we can say, where do we want to spend the money? Do we want to spend the money on reducing the self-support? Do we want to spend the money on reducing the fraction? Or do we want to spend the money on increasing the capacity?
Yep. Like it.
Great, great. Okay, well, it's been a pleasure, and I'll stop the recording now, and I'll send it to you and Michael and Coyote.